Limits at infinity with rationals. Let us recall the familiar function y equals 1 over x. Here's what it looks like. The limit of 1 over x as x approaches negative infinity is equal to what value? And what do you think the limit would be of 1 over x as x approaches positive infinity? Well, if we actually read the graph, as x approaches negative infinity, 1 over x gets closer and closer to 0. And as x approaches positive infinity, the limit of 1 over x is also equal to 0. And notice that they're hugging the x-axis in both directions. Sure, it's easy to find a limit of rational functions when a graph is provided, but what would you do without a graph? To solve the previous example algebraically, we need to consider the indeterminate form of 1 over positive or negative infinity, which is what would result if we were to use substitution here. As the x value approaches either infinity, whether it be positive infinity or negative infinity, the value of the function gets closer and closer to 0 because 1 over any very large number, in other words, 1 over 10,000, 1 over 100,000, etc., is so small that it can be considered 0. Hence, the limit of 1 over x as x approaches negative infinity is equal to 0, and the limit of 1 over x as x approaches positive infinity is equal to 0. The same algebraic reasoning can be applied to finding limits at infinity of any function in the form where c is a constant. The limit of c over x as x approaches positive or negative infinity is equal to 0. Similarly, adding or subtracting a constant from the denominator would not change the fact that the denominator approaches infinity while the numerator stays constant. Therefore, adding or subtracting a constant from the denominator of a rational function would also result in a limit of 0. In other words, the limit of c divided by the quantity x plus c as x approaches positive or negative infinity is also equal to 0. With a graph, when a limit goes to infinity, we look for any horizontal asymptotes. But what happens if we're not given a graph? When there's no graph, we look for a number of possible results from direct substitution. Here are a few examples that we'll examine further. The first example, or the limit of x squared as x approaches positive infinity being equal to positive infinity, that isn't a problem to understand. When you know the end behavior of a polynomial, the limit as x approaches positive or negative infinity is positive or negative infinity, respectively, depending on the highest degree of the polynomial. In other words, the limit of the polynomial x cubed minus 2x squared plus 3x plus 5 as x approaches positive or negative infinity would be the same as the limit of x cubed as x approaches positive or negative infinity. As an odd degree polynomial function, the end behavior would be the limit of x cubed as x approaches positive infinity is equal to positive infinity, and the limit of x cubed as x approaches negative infinity is negative infinity. In other words, x cubed polynomials have end behavior that looks like this, which again makes finding their limits a lot easier. But what about the other two examples that are shown below again? Not all infinities are the same, meaning infinity divided by infinity is not equal to 1, and infinity minus infinity is not equal to 0. How would we evaluate or understand the end behavior of this rational function when we're taking the limit of 3x plus 5 divided by the quantity 6x plus 7 as x approaches positive infinity? Since direct substitution clearly doesn't work. Let's first discuss this one, or the rational function scenario that's given to the left. For general rational functions, direct substitution will not work because you will always get a result of positive or negative infinity divided by positive or negative infinity, which doesn't really help us. So instead, there are three rules that will help us find limits as x approaches positive or negative infinity of these functions. The rules are directly related to those that we use to find horizontal asymptotes of general rational functions. Rule 1. If the highest power of x of a rational function appears in the denominator or is bottom-heavy, then the limit of f of x as x approaches positive or negative infinity is equal to 0. This rationale can be shown with any example of a general rational function whose highest degree is in the denominator. For example, the limit of the quantity x cubed minus 2x plus 5 all divided by 12x to the 6th plus 2x to the 4th minus 3x minus 11 as x approaches negative infinity. Let's start by dividing each term of our rational function by the term that has the largest exponent. This seems to complicate the function, but it will help us in the end. So for example, in our rational function that we have here, the highest exponent is x to the 6th. So we are going to divide each and every term, not just in the denominator, but also in the numerator by 12x to the 6th because it has that highest degree. When you simplify each term from the division, the result is shown below. Recall from earlier our limit properties, which allow us to take the limit of each term individually as well as the limit of c divided by x as x approaches positive or negative infinity being equal to 0. Because this is true, for every single fraction that we have, or every single rational expression that we have in the overall one, we can substitute 0 in for each of these. Therefore, the limit of 1 divided by 12x cubed minus 1 divided by 6x to the 5th plus 5 over 12x to the 6th, all divided by the quantity 1 plus 6 divided by x squared minus 1 over 4x to the 5th minus 11 over 12x to the 6th is equal to 0 minus 0 plus 0 all over 1 plus 0 minus 0 minus 0, which would be 0 over 1, which equals 0. Now that we understand that rationale, in the future, the procedure becomes very easy because any non-leading terms will just cancel out or approach 0 at a much faster rate than the leading terms. So therefore, the limit of this rational function as x approaches negative infinity is equal to the limit of x cubed divided by 12x to the 6th as x approaches negative infinity, which is equal to the limit of 1 over x cubed as x approaches negative infinity. And then if we substitute negative infinity in for x cubed, we get 1 divided by negative infinity, which is equal to 0. So this proves why Rule 1, if the highest power of x appears in the denominator or is bottom-heavy, then the limit of f of x as x approaches positive or negative infinity is equal to 0. Rule 2, when finding infinite limits of rational functions, if the highest power of x appears in the numerator or is top-heavy, as we call it, then the limit of f of x as x approaches positive or negative infinity will be equal to positive or negative infinity. The resulting sign of the infinity will be whatever the overall function sign results in from substituting. We're going to look closely at examples on the next pages or slides to understand this rule a little bit more clearly. Let's consider the limit of x cubed divided by x squared as x approaches positive infinity. When we use direct substitution, we will find that it equals positive infinity divided by positive infinity. Is the limit 1? It's actually not, because as we have seen, if we reduce the rational expression before substituting, we'll end up getting something even simpler. We'll get the limit of, well, x cubed divided by x squared is just x. So we'll get the limit of x as x approaches positive infinity. And that's equal to positive infinity. Let's use that same rationale to prove rule 1 to examine this a little further. Let's consider the following example. The limit of 5x to the 7th minus 2x to the 5th plus 15, all divided by the quantity 2x to the 4th minus 21x cubed plus 3x as x approaches positive infinity, as well as the limit of the same rational function as x approaches negative infinity. In the cases above, the function will behave similar to the function y equals 5 halves x cubed does when x approaches either infinity, positive or negative infinity, after being simplified. In other words, we can use that crossing out of lower degrees strategy that we did in rule 1 to make the limit of our rational function as x approaches positive infinity to simplify to the limit of 5 halves x cubed as x approaches positive infinity. And if we substitute positive infinity in, positive infinity cubed is still positive infinity, and 5 halves of that is still positive infinity. So that's showing us or justifying the fact that the end behavior on the right-hand side is going to be going upward and in the positive direction. Similarly, as x approaches negative infinity in this function, we can again use that simplification process that we did before to have the limit of 5 halves x cubed as x approaches negative infinity, which would be equal to 5 halves times negative infinity, using the direct substitution here, which would be negative infinity. And that's justifying the left end behavior of our simplified or reduced function that this one will generally model. Some of its zeros will potentially be different, but it will have the same end behavior as 5 halves x cubed, which would be increasing to positive infinity to the right and decreasing towards negative infinity to the left. Let's also try to verify these graphically. So I've entered both our original function into Desmos, so it's showing up in red here. And then we said that its end behavior sort of resembles the end behavior of this one. Well, I can definitely see how, as x approaches negative infinity, our function values for the red function, or our original rational function, approach negative infinity. But this one, actually, within this viewing window, appears that as x approaches positive infinity, the function would approach negative infinity, which is not what this resembles. So let's actually see what happens if we continue to zoom out. Zoom in and out. So I know I see, I think something else came into play here. So let me try to keep the y values the same, but change our x values to still be that negative 15 that we had before. See what this looks like. Oh, there we go. And then I zoomed out even more. Look. So this approaching negative infinity was happening because of an asymptote. And way up here, it picks up. It's approaching positive infinity as it gets to that asymptote. And then it curves in. And now, if we put this back in, we can see that it does kind of resemble this simplified function. So as our x value is approaching positive infinity, our rational function is indeed approaching positive infinity. So this is also a reminder that within your calculator viewing window, adjustments will probably need to be made to clearly show how, or to show how it resembles the polynomial, but also to find those limits. So just keep in mind that sometimes your viewing window may not show all of the necessary asymptotes required. So it helps to zoom in and out to see what the entire function looks like. Rule 3 for finding infinite limits of rational functions states that if the highest power of x appears in both the numerator and denominator, in other words, their powers are equal, then the limit of f of x as x approaches positive or negative infinity will be equal to the coefficient of the highest power in the numerator divided by the coefficient of the highest power in the denominator. Let's consider the limit of the rational function 3x plus 5 divided by the quantity 6x plus 7 as x approaches positive infinity. As we've done before, we can take the highest power of x in our function, which is just x to the first, and divide each of our terms by it. If we do that, we would be looking at the limit of 3x over x plus 5 over x all over 6x divided by x plus 7 over x as x approaches infinity. And then the 5 over x and the 7 over x cancel each other out. And these x values actually cancel out in both the numerator and denominator. So because these simplify, you could consider it being equivalent to the limit of 1/2 as x approaches infinity, which is 1/2. So as before, the constraints in the numerator and denominator would not affect the limit from that of 3x divided by 6x, which simplifies to 1/2. And once it's simplified, it becomes a constant function whose limit is the same as the quotient of the leading coefficients. 3 divided by 6 is equivalent to 1/2. So here's a summary for limits approaching positive infinity. The limit of f of x as x approaches infinity and the limit of f of x as x approaches negative infinity. If the higher degree is on the bottom, then the limit will automatically be 0. If the higher degree is on top, the solution will either be positive or negative infinity, and it's based on the end behavior of the simplified polynomial function that you have. So you could have two or both sides going towards positive infinity. You could have both sides going towards negative infinity. You could have the right side going to positive infinity and the left side going to negative infinity, or you can have it be reversed. You could have the left side approaching positive infinity and the right side approaching negative infinity. So it all depends on the end behavior of the resulting polynomial function degree. And then if the rational function has equivalent degrees in both the numerator and denominator, then the limit of f of x as x approaches positive or negative infinity will be equal to the coefficient of the leading terms. In other words, you're going to have a horizontal asymptote that is equal, that has the equation y equals the coefficient of the leading terms. That's going to be your horizontal asymptote.